Hello everyone. So in this video we're going to be talking about how to solve something called initial value problems. So what you might have noticed is that when we've been looking at indefinite integrals so far, okay, if I look at the indefinite integral of f prime of x dx, that will give me some function f of x, or the antiderivative of f prime of x, plus this constant c. And you might be asking yourself, how do we find this constant c? Well, that's what initial value problems are all about. This solution, if we leave c as it is, this is called the general solution. And if we solve for that c, we get something called the particular solution, or I like to call it the real solution. We have no more unknowns in the function anymore. Okay, so remember how when we want to describe an equation of a line, we need a point and a slope? Well, if we want to find an equation of a line given a derivative, really what we need is not a slope, but a function of the slope, which is the derivative, and a point, okay? So notice in this case, they're telling us, okay, f of x at some point x naught is equal to some value f naught, okay? These are just symbols. It's basically just saying I have an x and a y value for my function, and I also have a derivative. If I find the antiderivative of that derivative, I will get the function plus c, which is my general solution. And then if I go through and find the c, I get my particular or my real solution. So the way that we go about doing this is, first of all, we just solve the indefinite integral. We just do what I did right up there, okay? Then we use this initial condition. We know that at x equals x naught, if we plug that into our function, we know that will equal this number that I call f naught. We can use this to find what that constant c is. Now, once we've found the constant c and we have all the pieces to the puzzle, we have the particular or the real solution to the problem. So let's look at an example of this. So try to do this one on your own without my guidance, okay? Give it a shot. Okay, so if you tried this one, obviously this is our derivative function, and this is our what we call our initial condition. I'll write that down here. That initial condition, remember, is our point that our function touches, and we need that point to determine the full equation for the function to solve for that constant c. Okay, so the first thing we want to do is we want to evaluate our indefinite integral, which is going to be 2x squared minus square root of x plus 1 dx. If you go through and do that, you will get 2/3 x cubed minus 2/3 x to the 3/2, remembering that square root of x is the same as x to the 1/2. Then I just apply the power rule to that. Then we will have plus x, and finally plus c. So now what we got to do is solve for that c. So if you did not get that indefinite integral correctly, why don't you start from here and figure out how you would solve for that value c. All right, so what we would do to solve for that value c is we know that when x is equal to 2, our function is equal to 4. So what we'll do is set 4 is equal to 2/3 2 cubed minus 2/3 2 to the 3/2 plus 2 plus c. And check that out. We have everything we need here to find for that constant c. So it's just a little bit of arithmetic after that. But if we get that, we should get that c is equal to what I got. Again, not using a calculator. You should try to do all these without using a calculator. It's great practice. You might get an answer slightly different than mine, but just plug your answer into your calculator or just see if you can convert it to my answer to make sure you got the same thing that I got. But this will be 4 square root of 2 minus 10 over 3. That's what I got as my value for c. So therefore, this function can be written as our particular solution, which we'll call f of x. That will just be 2/3 x cubed minus 2/3 x to the 3/2 plus x plus 4 square root of 2 minus 10 over 3. All right, so that's what we end up getting for our solution there. Again, if you want to have more practice on this, just come see me. I can give you tons of book problems where you can practice this thing. I would highly recommend practicing these, especially just getting that practice of doing these without a calculator. is really, really, really helpful, and it helps kind of solidify a lot of really good math skills in there as well. So as a last example, I'm going to do one that's a little bit more fun. Okay, so we got an acceleration of an object along the x-axis, meaning it's moving in a straight line. So we're talking about one-dimensional motion. It is constant at what we will call a sub x. So we have a constant acceleration. We know that its velocity and position along that line at t equals 0, meaning the initial velocity and position at our initial time are just v naught and x naught. We'll just use those symbols. What we want to do is determine the position function x of t in terms of these variables right here. So see if you know what you have to do that. Pause the video, try to give it a shot. Okay, well, first of all, hopefully you would have pieced together that if we want to find a function for velocity, we are going to have to take the antiderivative of the acceleration function, okay? So this is just going to be the antiderivative of a sub x dt, which is a constant. So that antiderivative is just going to be a sub x times t. This is actually just using the power rule, okay? So in this case, the power is to the 0th power. So then the power becomes to the first power, and that's how that works out, okay? So we get this, and then we have plus c. We have plus our constant. So what initial condition are we going to use to solve for that constant? Well, we have this. We have v at 0 is equal to v naught. So if we utilize that initial condition, we will get v naught is equal to ax times 0 plus c. This gives c is equal to v naught. So therefore, our velocity function is given by ax t, or actually let me write it this way so it'll look a little bit more familiar to people who are currently in the AP Physics, or even the, actually I don't know if the general physics class looks at equations in this way. But anyway, this will be v naught plus a sub xt. So people in AP Physics, this should look like a familiar equation. Okay, so we've done half of it, all right? If you weren't able to get this far, pause the video now. Now see if you can apply the exact same method to find what our position function will be. Okay, if you gave that a shot, we would have said, okay, well, position, that's going to be the antiderivative of velocity, which will be the antiderivative of v naught plus axt dt, all right? So if we want to find this antiderivative, v naught is a constant, so that's just going to give us v naught t when we evaluate the antiderivative of that. Axt, again, we're going to use the power rule. This is like t to the first power. So when we take the antiderivative, we will get 1/2 that constant ax times t to the second power. And now we have this plus constant. So we got to utilize another initial condition. And in this case, we have the given initial condition that x of 0 is x naught. So if we apply that, we get x naught is equal to v sub 0 times 0 plus 1/2 ax times 0 squared plus c. This gives us c is x naught. And if I finally write out this entire equation, I get x of t is x naught plus v naught t plus 1/2 ax t squared. Now people in, again, the AP Physics class, this should look like a very familiar equation to you. Maybe you guys remembered looking at this equation in an Algebra 2 class or something when you were talking about parabolic motion. Maybe you always wondered, why in the world was that 1/2 in front of the acceleration term, and why was the acceleration term squared? Well, now you know. We just got that answer by applying calculus. And it turns out what we did right here is one of the best applications of calculus. What we ended up doing was solving something called a differential equation, which we will talk about this in a later unit. But this is an incredibly powerful tool. This is how mathematicians, physicists, engineers, what have you, this is how we figure out how we can model the trajectory of various objects that are influenced by forces. Recall that forces are proportional to acceleration. So therefore, if we have acceleration, which in itself is a derivative of velocity, which is a derivative of position, so acceleration is a second derivative of position, we can basically integrate that second derivative or integrate that net acceleration of something twice in order to get what its position will be at any time. How do we find the net acceleration? Well, other people in physics, and if you're not in physics, I apologize for this divergence, but we have this little law. Sum of forces is mass times net acceleration, okay? So by using Newton's laws, summing up the forces on something, which is very easy to do, we can come up with what's called a second order differential equation, or an equation that measures the acceleration of something, integrate it twice, and we can get its position. Pretty cool stuff. So I'll talk more about some applications of this in class, but for now, hopefully these examples were useful, and please come to class with questions.